Welcome back to the 10th video about the Melexis MLX90363 Triaxis magnetometer. In the previous video, we finished the basic implementation of our library by implementing the last two messages that thing understands for measuring its internal oscillator frequency. Card here, link in the description. Today I want to start out with some housekeeping in regards to the library. You know, there are some things that I don't like about it, and I want to improve a little bit our frequency measurement of the internal oscillator. It works, but it's not very precise, so I want to make that better too. And after that, I want to start looking into the different configuration parameters and what they actually do. Enjoy! So let's dive right in. You remember how I moaned about that my class starts with a short private section containing the enum class marker, the enum class meso opcode, and the array of the valid meso opcodes. I needed these three private definitions because then, when my public part starts, I'm using them to define my enum class received. And in C++, there is no way to defer the declaration of the marker and the meso opcode to another place. It has to happen before you use them. In the new version of my code, my class starts right away with the public part and the enum class received. And the drawback here is that I don't have a constant for the markers. I have to use the numeric value or define the numeric value for the opcode of the other messages somewhere, so I can do it as well here. But I have to admit, having here to use the marker repeatedly without a constant or a num for it is a little bit My enum class marker went to the private part in my class definition at the very end. And there I do repeat the bit patterns for the 4 different markers, which, as I said, is a little bit but it's better than having that a short private section at the start of the class, at least in my opinion. What you also should notice is that the enum class meso opcode is completely gone because I don't need it anymore. In the old code, I used the meso opcode only in 2 places. First, to fill up my array of valid meso opcodes, and for the definition of my enum class received. Well, in the new code, we already have defined our enum class received using numerical values. And the only place where I use that constant meso opcode array here is in the implementation of the private method valid meso marker opcode, where when the marker is other in a meso message, I loop through the whole array and check if the opcode in the meso message is actually a valid one. In the new version of the code, I moved that array into the method valid meso marker opcode because that's really the only place where it's used and there's no need to clutter up the class definition with that array. Also, it's no longer an array of meso opcodes, but an array of received enum members, which I directly cast here in the constant definition of the array to unsigned integer 8. And thus my loop further down here doesn't require any use of a bit mask or any cast operators to work. So it's less code, it's faster, it's better. Okay, next improvement. That is, I really just renamed stuff. We're in the old version of the code, and there we have send methods, which send over MOSI messages to our chip. And we have last methods, which we can use to retrieve data from the last meso message that we received from our chip. First one being here, of course, last received. That gives us the type of the last received meso message, and then it goes on here. Last get diagnostic, for example, which gives us the diagnostic from the last received get message. That last prefix never really sat well with me because we have sent and then we have last. So I renamed all these methods now received. Now we have sent and received. Makes much more sense. And the first two methods here, that was last received in the old version of the code. And now in the new version of the code, it's just received and it returns us the type of the received meso message. And here the diagnostic for a get message is now returned by a received get diagnostic. I like it better. Finally, we have another improvement. Well, it's just a little name change. You remember in the, I think it was the 7th installment, card here, link in the description, I had difficulties naming all the MOSI and meso messages in regards to writing the EEPROM. And I came up for, according to the datasheet, the EE read challenge, respectively EE write read challenge message here, with the name EE requesting, and I came up with a really convoluted reason why there should be an ENG here at the end, and I deleted that. So the MOSI message type is now called EE request, and the associated method is now called send EE request. That's it. That was enough housekeeping for today. Now let's move on to the new and improved oscillator frequency measurement. For how that works in principle, see the previous video, already carded, link in the description. Anyway, to calculate the oscillator frequency, we use that formula here. And the critical part in this formula is that T oscillator counter. So the time we let the internal oscillator counter of our chip run. And the chip returns us the counter value. And that T oscillator counter time is defined as the time between the rising edge after we send our oscillator start MOSI message and the rising edge after we send our oscillator stop message. And in the previous video I stated this is probably quite hard to measure exactly in Arduino land, because we implemented here a send oscillator counter start method, a send oscillator counter stop method, and well, now called received oscillator counter. So the timing of these rising edges on the slave select line are deeply buried within the library, and when using the library we do not have any access to it. However, if I started thinking a little bit outside the box of send and received methods, I came up with a pretty good solution. Just so we can compare it to the new and improved solution, here is the loop from the sketch from the previous video we used to measure the oscillator frequency. So we use send oscillator counter start to start the oscillator counter in our chip, and then we wait a little bit, and then we use a send oscillator counter stop to stop the counter in the chip again. And then the next time we do a send oscillator counter start, we receive an oscillator counter stop meso message from that chip containing the counter value. And yeah, T oscillator counter, so rising edge to rising edge, was just guesstimated. not very good. To get an accurate measurement between the two rising edges on the slave select line, I had to modify our low-level send method, which does all the SPI stuff. And here, after I do a digital write to the slave select line, setting it high again, I inserted here a timestamp statement, writing the actual time in micros, so microseconds, to a new private class variable SPI SS pin high. And I'm using this only for oscillator counter measurements. It has no other purpose and it slows the send method a wee bit down, but yeah, that's the price we have to pay. Here's that variable in the private part of my class definition, so it's really just a timestamp when the slave select pin was set high. And please also note that all the oscillator stuff we used in the sketch last time is now private. Instead, the library provides a new public method, info oscillator frequency megahertz, name subject to change, which returns, of course, the oscillator frequency in megahertz as a float and gets as an argument the sample time, so between oscillator counter start and oscillator counter stop, in microseconds, which defaults to 16,383. Why, we see in a second. Then we have two local variables here, a timestamp and T oscillator counter, both unsigned integer 32. And first of all, we check if our argument to the function was smaller than 500 or greater than the default value. In that case, we stop and return not a number. Again, I'll talk about these limits in a second. Then we do a send oscillator counter start, and if that fails, we also do a return, not a number. And then we take a timestamp of our private class variable SPI/SS pin high, which was set during the send oscillator counter start when that method called our private method send, and send set that timestamp here, which we just copy. Then we do a delay microseconds of our sample time, and here comes the upper limit. So according to the Arduino documentation, delay microseconds only works accurately in the range up to 16,383. Then we do a send oscillator counter stop. And if that fails again, we return none. And that method also, via the called send method, sets our SPI/SS pin high variable. And then we can simply calculate in a very precise manner, not absolutely precisely, but quite precise, our T oscillator counter by simply subtracting the timestamp we took before from our actual time we set the slave select line high. And here comes our lower limit of 500 microseconds. That's a constraint from our chip. So T oscillator counter time should be a minimum of 500 microseconds. Then we do a delay of a T short, just so our chip is happy. And then we send a knob. If that fails, again, we return not a number. And if we not received the oscillator counter stop message from our chip, then something went wrong. And we do a last library error opcode. And I forgot here return none. Sorry for that. Otherwise, we just return the result of our formula, and this time we use a quite precise T-oscillator counter. The loop in the new sketch to measure the oscillator frequency in megahertz is quite simple now. I just serial print the return value of the info oscillator frequency megahertz method with 3 digits after the decimal point and do a delay 500 in between. And here's the result on the serial monitor, and you see right away that we only have very tiny fluctuations. So I'd say, yeah, maybe here on the second digit after the decimal point, but mostly only here on the third digit after the decimal point. So our measurement is at least very stable. If you compare that to the previous version, that gives us about 19 point something megahertz. And in the next round, it's 18.55 megahertz. You'll see that we made a real improvement there. In the last video, I stated that the oscillator frequency should be 19 megahertz, which was a blatant lie. If I would have looked into the timing specification in the datasheet for 5-volt applications, the main clock frequency we are measuring should be between 15.2 and 18.8 megahertz. So with the 17.0 something megahertz we're currently measuring with the new code, we're pretty much here in the middle, so spot on. And yeah, that's quite a wide range. That thing doesn't contain a quartz, it doesn't have an external quartz, and I highly doubt that they use a laser-trimmed RC oscillator. It's probably just a chain of inverters in series with a feedback loop to generate that clock. By the way, when running that thing with 3.3 volts, the minimum main clock frequency is even lower. So the clock frequency range is even larger. Now, onwards to the configuration options. But before we dive into the details, some basics about how the measurement axes of that chip are defined and about magnets and field lines in general. In the Getting Started guide, we find that picture here that defines the x-axis, the y-axis and the z-axis. It's probably coming out of the paper, so going up for our package. Pin 1 is here, by the way. It also says that the axes of the MLX90363 are defined in the datasheet and are shown below. However, if you look into the datasheet, you have almost the same drawing here. The z-axis, respectively the direction of the z-axis, is missing here. Anyway, in the following, I will draw the north pole of magnets always as red, the south pole always as green, and the magnetic field lines in a direction that go from the north pole to the south pole. Our little chip sits like that on the edge of our breadboard on its breakout board. So here is pin 1. So according to the datasheet, x-axis should be in that direction and the y-axis should be in this direction and z going up. And if there's one thing that we've learned so far, it's that Melexis datasheets are first comprehensive and second correct. Therefore, we will first do some measurements to see what axis is really what. For that purpose, I acquired some new magnets. Unlike the magnets I used before in my videos, which are radially magnetized, that is, one half is the North Pole and the other half is the South Pole, these are axially magnetized, that is, one end is the North Pole and the other end is the South Pole. To determine that, we can use a compass. Please note that the red part, which is marked north of the compass needle, is pointing to the North Pole of the Earth. So this is really the magnetic South Pole of the needle. Okay, so putting my stack here, the needle is pointing to the North Pole. So this is north of my stack. And if I turn it around, the part of the needle that's usually pointing to the South Pole of the Earth, so the North Pole of the needle, is pointing to the South Pole of my stack. I've marked out both ends of my magnet stack according to our convention, which is a usual convention, by the way. And now I can remove that magnet here, put those far, far away. And we just insert that into a little Lego Technic piece. By the way, I use these in quite a lot of projects, but with the radially magnetized magnet, links in the description, maybe a card here. And then we put that onto a stick, and then we have a magnet on a stick, which we can use to probe our chip. Let's make some measurements then, shall we? For that purpose, I modified the setup in the sketch a little bit. I commented out the serial print here with the press enter to start because I want to use this time the serial plotter and it doesn't like printed out text. And I added at the very end some names for the 4 values we will show on the serial monitor. X, Y, and Z are self-explanatory, but I will also plot out a 0 line for visual reference. In the loop, I first do a send get one XYZ to request XYZ data from the chip. Then I wait for appropriate time so the chip can make the measurement, and then I send a knob so we can receive the XYZ data from the chip, which I then serial print to my serial monitor, and finally I always print a 0 value for our 0 line. And then I wait 500 milliseconds and we do the whole thing again. So let's measure. Press enter to start, and what we can see here right away is that I don't see my zero. My zero is at the very top, and we have here comparably small negative numbers. Remember, these values here are signed 16-bit integers, so approximately plus minus 32,000. And we are here now here at green, that's the z-axis, at minus 150. Anyway, according to the datasheet, this should be the x-axis, so I approach here with my North Pole, and blue is, let's center that up. Yeah, positive spike on blue. Then if I come with the North Pole from the other side, we should get a negative spike on blue, the X value, yes. And if it's all documented correctly, if I come from that side with the North Pole, that's the Y value, the red curve, yeah, positive value. And then from the other side, reversing the field lines, yeah, strong negative value. And that leaves Z from the top, that's the green one. Yeah, center it up correctly. Yeah. Positive spike on Z. And if the field lines come from below, let's try that. That's a little bit tricky. But yeah, we can see there's also a negative value now on the Z plot. Perfect. Turns out the datasheet was correct this time, if a little incomplete. So here's the x-axis, here's the y-axis, and here is the z-axis. We just verified that, and what we learned is if the north pole is at the end of one axis, as I've drawn them in, then we get a positive value, so with the field lines going to the center. And if the south pole of a magnet is at the end of these axes, so the field lines going away from the center, we get negative measurement values. Great. The video is already getting quite long, but I said in the beginning that we would start covering the parameters, and so we shall. And we shall start at the very beginning with VIRTUALGAINMAX and VIRTUALGAINMIN. Basically two parameters, and they are really at the very beginning, as you will see. VIRTUALGAINMAX and VIRTUALGAINMIN set the what Melexis calls electrical gain code maximum and minimum. Max has a default value of 41, min of 0, and they are both 8-bit values, unsigned integer. It's never stated explicitly anywhere, but you can defer it from the context. The related chapter explaining the parameters is really brief, 4 lines, and it says that VIRTUALGAINMIN and max control the automatic gain control loop. That's something we know, automatic gain control. Many microphones have an automatic gain control, so if you speak very quietly, then the gain is increased and it gets louder again. But when you speak very loud, the gain is reduced again automatically, so that you are at an almost constant decibel level. The electrical gain code, that's probably a multiplier going into that automatic gain loop, is limited to a range within VIRTUALGAINMIN and VIRTUALGAINMAX. If you set VIRTUALGAINMIN equal VIRTUALGAINMAX, then you have a fixed gain. Also, these two parameters influence the diagnostics D17, field magnitude too high, and D18, field magnitude too low. If we look at the two diagnostic bits D17 and D19, we can learn something more. So D17 means field magnitude too high. Norm is greater than 99% of the analog to digital converter span. And footnote 19, where it says norm is the maximum of the absolute of x, y, or z, meaning norm is the absolute of the largest field magnitude we measure in any direction. It also says here that the automatic gain control keeps norm below 63.5%. D18 is consequently field magnitude too low, so the norm is smaller than 20% of the analog to digital converter span, and the automatic gain control tries to keep norm above 47%. There is a chapter automatic gain control which provides some more tidbits of information. So it says here the virtual gain code is updated at every get message. So that's not something running in the background. You have to send a get message to your slave. And that the new code is based on the field strength norm, which is not explained here, of every raw component XYZ. Yeah, we saw that. It also says that the automatic gain control makes sure that the norm is between 47 and 63.5%. We also saw that in the D17, D18 diagnostic bits. By controlling the gain code within the range virtual gain min, virtual gain max. Yeah, we knew that already. But here comes something. The algorithm gives a limitation in term flux density frequency. See sections 10 for specification. We will have to do that. And that's most important when programming and using that chip. It is not recommended to interrupt the get message sequence because AGC iterations are triggered by get messages. Yeah, we already saw that it's updated at every get message. So you have really to do get. Otherwise, that whole mechanism doesn't work correctly. And if a pause cannot be avoided, you need to ignore the 6 following get messages. Yeah. The magnetic flux density frequency is of course not given in chapter 10, but in chapter 9. 9.2 contains the values for 3.3 volt operations, and that's from 9.1 for 5 volt operations. And to be honest, I can't make sense of these numbers here. Somebody better than me has to interpret these. But interestingly, there are 2 more footnotes. So in general for the sine wave flux density. And then we have that table here basically doubled. Once here with no footnote and then with footnote 4 with a different Hertz values as a maximum. Footnote 3 says sensitivity monitors enabled. See section 17. We had a look at that before, but we will do again. Beyond that frequency, the sensitivity monitor must be disabled. Contact Melexis for more details. And footnote 4, limitation linked to the automatic gain control. Beyond that frequency, there is a reduced immunity to norm change, e.g. through vibration. See also section 18.4. Yeah, we just looked at 18.4. So, interpreting this, the top 3 lines are the limits in regard to the sensitivity monitors when they are enabled. And you have to disable them when you go beyond these frequencies. The lower 3 lines are the limits linked to the automatic gain control, which you can also disable by setting max and min virtual gain to the same value. We're back in chapter 17, looking at the BZ, BX, and BY sensitivity monitor diagnostic bits D12 to D14. We covered all these diagnostic bits when we talked about the diagnostic messages. Card here, link in the description. Anyway, we are immediately sent back to see the magnetic frequency specification. We're really going in circles now. But if you remember, we had here that footnote 18, and that states that the sensitivity monitoring is disabled in 3.3 volt operation. So, and that's the only way you can disable it. Yeah, run the chip at 3.3 volts instead of 5 volts. It's not really programmable. Also, the BZ sensitivity monitor was always disabled and you have no way to enable it. That's why they mention to call Melexis for more details. They have to do some black magic undocumented programming on these things to disable the stuff here in 5 volt operation or to enable the BZ sensitivity monitoring, I guess. And here's the reason why I stated in the beginning that these parameters are at the very start. They are at the very start of the signal processing. So we have here the inputs from our 3 analog to digital converters, and then here the automatic gain control is immediately applied before we can get the X, Y, and Z values with our get message. There's another block here, but we will talk about that in a future video. Enough of the theory. Let's do some experiments, and for that purpose I modified my sketch a bit. So, in the setup, after the begin, I have now here update statements for my virtual gain parameters min and max, 4 of them. First, we try out the defaults, that is min 0, max 41. Then we will try a minimum fixed gain, so min 0 and max 0, then a maximum fixed gain, min 255, max 255, and finally a max dynamic range, so min set to 0 and max to 255. And after that I do of course a commit config and handle an error if some should occur. I also extended the serial print statement here. I will not only print X, Y, and Z and the 0 line, but also that norm which I calculate, and also a minimum and maximum value of a signed 16-bit integer. That's just so that the scale of the plot doesn't jump around as the values of X, Y, and Z change. Finally, I do here already in the setup a send get one X, Y, Z. You will see in a second why, and if that fails, I do of course error handling. In the loop, I first delay for 30 milliseconds, so the chip has time to actually do the measurement we requested in the setup. Then I do another send get one XYZ, which should receive from the chip the result of the first measurement we requested, some error handling if necessary. And if we really received XYZ data from the chip, then I print everything out, including the norm on which the automatic gain control is based. Otherwise, yeah, some error handling. I can't increase the delay here over 30 milliseconds. I know that the whole loop stops working if I increase it to 40 milliseconds because remember, we have a data timeout on the data we request from the chip, which is roughly 65 milliseconds. And with all the serial print and stuff going on here, we end up as a maximum delay of 30 milliseconds. You also notice that I don't use knobs here in the loop like before. That's because the datasheet clearly states you shouldn't break the string of get messages, otherwise the automatic gain control wouldn't work properly. And here's how the whole thing looks on the serial plotter. So our data lines X, Y, Z and norm are always here around the 0. Here is our minimum integer value, here's our maximum integer value. And now let's get a magnet into the play, and I'm approaching here and you see, oh, we already get a signal. That's of course on the X line, which you can't see the blue because it's overlapped by the norm line, which is the X line currently. So let's go closer, slowly, 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 and yeah. We see these little jumps here, and now I'm very close and we see some kind of oscillation. We can see this oscillation again if I go just a step back. Then it just wiggles a little bit until the automatic gain control has adjusted to the new strength of the magnetic field. Let me correct here a little bit on the X. No, that's the Y-axis, so we get that to 0. If I jump closer again, yeah, you see the oscillation here on the automatic gain control, which we don't see if I really move. I'm trying to move really slowly. Doesn't really work. Yeah, here it works. And now we're, distance-wise already out of the range of the automatic gain control because our level is sinking. So the automatic gain control can't increase the amplification anymore. If we come closer slowly again, no oscillations. That is, we are within these frequency limits. Yeah, okay. Now that's vibration in my fingers here. Yeah, okay. Works as advertised. The value we get here is a little bit low. They set about 50%, 50% of the max ADC range, and we're here maybe at 10,000 instead of 16,000, so meh. Let's try that again with the minimum fixed gain. Okay, what we can see here with the magnet still in my hand, we have a lot less noise here on the data. And we are measuring stuff. That's because the amplification after the analog to digital conversion is now fixed to 0. At least it should be. So if I'm here at the very edge, you might see a little bit, not much. Let's go closer. Yeah, we're getting a signal. Now I'm really at the edge of my breakout board. Yeah, very small signal. But we can say that at a distance of about, here where my power rails are, our signal is almost 0. And if I really go to the edge of the breadboard, it's 0. So it's in this mode with a gain really turned down to 0, not very sensitive. Now let's try the same thing with the maximum fixed gain of 255. Right out of the bat with the magnet still in my hand, we see more noise. That's because we amplify the standard noise of the analog to digital converter by a factor of 255. I don't know. Let's approach here with the magnet, and I'm out of the picture, and here I am, and we already have a signal. And if we get closer and closer, and you see there is no wiggling. Automatic gain control is not there. It's really nice. If we go up close, we end up at, I'd say that's about 16,000 something as maximum value. And we already get into saturation. At which distance? I'm not interested in Z. I want to see X go down. There. Here, at this distance, about we're driving the thing into saturation. But the max value seems to be not 32,000 something, but 16,000 something. That's something to keep in the back of our minds. Now let's try the maximum range for the automatic gain control between 0 and 255. So we have about just the same noisy picture here as before when we had a fixed setting of 255. And we should see a signal out here. Yeah, we do. But if I go closer slowly, we don't get into saturation anymore, because now the automatic gain control is able to regulate the gain down to 200, down to 0. But what we also still see is if I move the magnet fast, going back here, we have the spikes. These small, these are only really short spikes, not really oscillations. But it takes, there we see some oscillations. It simply takes the automatic gain control a while, a few iterations. You remember the datasheet, they said to regard at least 6 iterations of the get one cycle until everything is settled in again. We're back to the defaults again. But I'm using the old loop structure with a get, a short delay in microseconds, and a knob to retrieve the data. And I also added here the min-max lines, but this time approximately minus 16,000 plus 16,000. And we have a delay of 500. So we are breaking the string of get statements, and we also have quite a heavy delay, long delay between the different get statements. And as we can see, data is now coming much slower. But what I wanted to show you here, if I go close to the chip, you see we're reaching the maximum line almost. But what I really wanted to show you is if I move the magnet fast, we have these spikes and these slight oscillations, exactly like we have in the loop where we just do get. With the difference, we don't do get, we do get, knob, wait a half a second, get, knob, wait a half a second. And the automatic gain control seems to work exactly like before. Yeah, it always tries to get to this sweet spot level here of around 50% of full scale. So I think the datasheet is wrong in that respect, that the gain control really needs get to work properly. Yeah, what else is new? That's it for today. Sorry that this last part about the automatic gain control and the virtual gain min-max parameters got so long. I think we already needed 9 minutes to shift to all the parts in the datasheet where relevant information about it could be found. But yeah, that's why I don't like the datasheet of that chip. Anyway, before I continue with the next parameters, I might slot in a teardown or two just to relax a little bit. So, till next time, bye.